Let's consider how to solve this system of 3 equations and 3 variables using Gaussian elimination with backward substitution. The first thing that we need to do is to rewrite this system of linear equations as an augmented matrix. So we want to use the coefficients. So we're going to have 1, 1, -1, and 12. -1, 1, -1, and 4. -3, 3, -4, and 15. Keep in mind our goal with Gaussian elimination is to rewrite this matrix so that there are 1s on the diagonal, there are 0s below the diagonal, and then some numbers in the other entries. So we'll work our way from the left side to the right side. So the first thing that we want to make sure is that we have a 1 in our first row and first column, which we already have. So now we'll work on this first column. We want to change these entries to be zeros. The way that we'll do this is by adding multiples of row 1 to the current row 2 and row 3. So since row 1 and row 2 have opposites in column 1, we're going to start by taking row 2 and adding row 1 to it to come up with a new row 2. So I want to take my 1, 1, -1, and 12 and add that to my current row 2. So my new row 2 is going to become 0, 2, -2, and 16. Now think about row 3. Row 3 currently has a -3. So what we want to do is we want to take our current row 3, and we're going to add a multiple of row 1. So since the opposite of -3 is +3, we're going to add 3 times row 1. So my current row 3 is -3, 3, -4, and 15. 3 times row 1 is 3, 3, -3, and 36. So we're going to add these together. So we get 0, 6, -7, and 51. This is going to be my new row 3. So the current matrix that I have, recopy row 1. So we still have 1, 1, -1, and 12 across the top. And now write down our new row 2, 0, 2, -2, and 16. And our new row 3, 0, 6, -7, and 51. So column 1 looks exactly how we want it, the 1, 0, 0. So now we move over to column 2. I first want to focus on turning this entry into a 1. So since it's currently a 2, the way that I can do that is by taking 1/2 times this current row 2. So each entry in row 2 is going to get multiplied by 1/2. So this is going to give us the new matrix of 1, 1, -1, and 12. Multiplying by 1/2, we now have 0, 1, -1, and 8. Row 3 is unchanged, 0, 6, -7, and 51. So as we look at our matrix, the first column is set. We now have the 1 on the diagonal that we want to have in row 2. So now we want to work on this entry that's currently a 6 here in row 3. So I want to use the row 2 where I just got the 1 in order to build this 0 that we need below it. So since it's currently a 6, I would like to add a -6 to it. So what I'm going to do is I'm going to take row 3 and I'm going to add to that -6 times row 2. So row 1 is unchanged. Row 2, I'm going to multiply by -6, add that to row 3 to replace row 3. So let's look at what that's going to be. So my current row 3 is 0, 6, -7, and 51. -6 times row 2 is going to be 0, -6, +6, and -48. So adding these together, we have 0, 0, -1, and +3. So this is my new row 3. So plugging in these values as my new row 3, we currently have this as our matrix. So as we look at column 1, it has the 1 on the diagonal, the zeros below. As we look at column 2, it has the 1 on the diagonal and the 0 below. So as we look at column 3, the one thing that's missing is we would like for this entry to be a positive 1 instead of a negative 1. So I'm going to just take negative 1 times row 3 to come up with a new row 3. So this gives us the matrix 1, 1, negative 1, and 12 in row 1, 0, 1, negative 1, and 8, and 0, 0, 1, and negative 3. So this is the end of the part of the process known as the Gaussian elimination. So now we are ready for the backward substitution. This matrix represents a system of equations. So remember, the first column corresponds to x's, the second to y's, and the third to z's, with the fourth augmented being our constants. So that first represents the equation 1x plus 1y minus 1z is equal to 12. The second is the equation y minus z equals 8. And the third is z equals negative 3. So that third equation is giving me the value for z, that z is negative 3. And now I want to take that and plug it into this equation that has just y and z. So if z is equal to negative 3, y minus a negative 3 is equal to 8. So if y plus 3 is equal to 8, then y is equal to 5. Now take the values for both z and y and plug those into our first equation to find a value for x. So x plus 5 minus a negative 3 is equal to 12. So x plus 5 plus 3, so x plus 8 is equal to 12, and x is equal to 4. So our solution as an ordered triple, x, y, z, will be 4, 5, and negative 3. So this is the process of solving a system of linear equations using Gaussian elimination and backward substitution.